I like to think I'm liked because I keep it real and I talk like a human rather than like an android, because I talk about shit I like.
You go 100 versus Jones.
There's no, I had 100% for a long time. Now I can go back up to 100% if the ratio's right. It needs to be above 99.5. It need, because they round, which means I need like a lot more to the 5 category is to cancel out the other ones.
There we go.
It's like a weighted thing.
We gotta get out of that. Yeah, I'll get it. We gotta write something good.
Alright. This is day 26. We are looking at, we're doing 15.1, which is on sequences. And 15.2, sequences and series in general, what they are. 15.2 will be on arithmetic sequences, a very particular kind of sequence. So in math, a sequence is an ordered list of numbers. Order matters. That we can write as a function. Whose domain or input values are positive integers. And I'm gonna say sometimes we will include 0 and a couple negative numbers. And the negs. But usually not very often, and probably we're not gonna do it in this class. Let me motivate this topic. Cause like when we're going through it, you're gonna be like, why the fuck are we doing this? So it turns out when you make it through Calc 2 and you start, if you study physics and higher, study physics. Light and sound travels in waves. That's, you're gonna study waves in trigonometry in pre-calc B. But there are functions that are not that easy to work with. But it turns out that we can write them as a series of polynomial terms. Which series is just taking the terms in a sequence and adding them together. So, like, we can take the hard math of trigonometry terms and turn them into something like x squared and x to the fourth and shit we know how to do fairly easily. So we take something hard and make it simple. And it's related to shit that's important in the world, like light, sound, energy, things that make the world go boom. So like, and I'm sure there's aspects, uses in other fields. I always like the physics one, so that's the first thing that comes to mind. All right, so. So I said we could write it as a function. We're gonna call that function f of n. And we'll call the output a sub n. So it's we'll kind of have like a sub 1, a sub 2, a sub 3, a sub 4, a sub n, depending on how high the list goes. Maybe I'll say a sub k. Seems kind of stupid to plug in n when n is already the variable. These are called the terms of the sequence. And the subscript tells you which term. Now, as you're going through this, and if you're like, some of this is awkward. Watch the video of the last hour. We did a lot of shit working with a lot of these, going on like deriving formulas, doing a whole bunch of stuff. Here, I'm gonna go through it a little bit faster. I will note that sequences can be finite. In length. Or infinite. So like maybe our sequence only has 10 numbers in it. Some sequences have an infinite number in it, like the Fibonacci sequence has an infinite number of terms in it.
How would you denote any infinite versus a non? What does it look like?
In terms of a sequence, I would do this. Or like an infinite one, I might keep showing more dots afterwards, the show goes on. Generally, dot, dot, dot at the end means it keeps going. And if there's not a stopping point, like here. This goes up to a sub k, this would be finite. And the infinite, I would have a sub k. Dot, dot, dot. That would be infinite.
It would be a continuous function.
It keeps going. So. Something to do together. Find the first four terms of. A sub n equals 3n minus 1. So the first term n equals 1. This is a sub 1 equals 3 times 1 minus 1 is 2. N equals 2. It's a sub 2. 3 times 2 minus 1 is 5. Go ahead and do n equals 3 and n equals 4 real quick. And then we'll do them together in like 30 seconds. This is not complicated mathematics. Three times 3 minus 1 is 8. 3 times 4 minus 1 is 11. So if I were to write this as a sequence. Two, 5, 8, 11. And you'll notice as we go from one number to the next, we're adding 3. Each time. When we do a process like this, it's called an arithmetic sequence. And that's gonna be what 15.2 is on.
Yeah, that looks familiar to me. It looks like something that I've seen like, the arithmetic sequence. We have.
Well, you like to look ahead. So you might look ahead and seen this part.
No, from like grade school.
Oh, okay. Of course, this guy here, Megan, this guy here, Keith. Comes into the fucking Mason Center and he's pulling out a fucking differential equations book. Differential equations is the last course of the math sequence. It's like fucking 6 courses from here. It's like, I just wanna look to see what's coming up ahead. It's like fucking reading Latin. Until you start going down the shit, it's like reading Latin. He's like, I just wanna look ahead. I'm like, bro, dude, you're fucking confusing yourself. Don't do this. That'll just make you not wanna do this.
You only like. Probably maybe 30,000 people speak Latin or something like that. It's like.
Well, that's even rarer than mathematics. This is for fucking Keith real quick. Let me find it. That's graduate level mathematics. It's actually, it's in the field of fluid dynamics.
Oh.
And notice the lack of numbers. Like all of this shit, they're all a bunch of equations. This is called a system of equations at an upper level. I got an equation here, there's an equal sign. I got an equation here. I got a bunch of equations, and just like the ones you guys have done, they all have to be solved simultaneously for every single variable. That's where computers come in. That's what I did in grad school. Yeah. Some rocket science shit right there. Straight up. That's 4 or 5 years later, you get on the map. But I know how to read it. I know what it is. I know what it's talking about. It's basic physics shit. All right. Next one. A sub n equals 2 to the n. Do the first 4 terms here. Yeah, you all saw this. We derived some of this shit earlier. So if I do this, a sub 1 is 2 to the 1, which is 2. A sub 2 is 2 to the 2, which is 2 times 2, which is 4. A sub 3 is 2 to the 3, 8. 2 times 2 times 2 times 2 is 16. So if I write them out as terms, one step to the next is a multiplier rather than adding. This will be 15.3. This is called a geometric sequence.
Geometric means multiplication specifically.
It actually comes from, I think, this is a very good estimate of where it comes from. A square is n by n. A cube is n by n by n, so n squared, n cubed, so we're going up powers. And these are geometric figures. I think that's where it comes from.
That makes sense.
In fact, these are why we call that being squared a squared number and a cube number. It comes from the geometric interpretation of it. I know that. All right, what about first four terms of a sub n equals -1 to the n over n factorial? Let's talk about n factorial real quick. So that is read as n factorial. So the exclamation point is factorial. And I think the simplest way to show you is 5 factorial is 5 times 4 times 3 times 2 times 1.
So it's just multiplied by every.
Every number lower than it until you get down to 1. It's only integers, it only works with integers. And we define 0 factorial to equal 1. And yes, mathematicians are aware 0 times anything is 0, but the primary equations this is used in is in probability and statistics. And 0 factorial pops up everywhere and there's no 0 in the answer. So we just use this shortcut notation, we say it equals 1.
But 1 factorial also.
1 factorial also equals 1, right? So let's look at this sequence right here. A sub 1 is going to be -1 to the 1 over 1 factorial, which is -1 over 1, which is just -1. A sub 2, -1 squared over 2 factorial is +1 over 2 times 1 is 2, so 1/2. -1 cubed over 3 factorial. An odd number on a -1 exponent or a -1 gives you a negative answer, and 3 factorial is 3 times 2 times 1, -1 6. So I'm going to write out the factorials over here real quickly for you for the first few. Because these never change, which is nice. If you see them in a pattern, you'll know that you're looking at factorials.
It's kind of like in chemistry, there's the valence shells on atoms, or like that. If you're gonna record how many electrons.
I'll take your word for it. I haven't been in valence shells in a long time.
Oh.
I remember them. I don't remember factorials in them.
Yeah, I know they.
So I go 1, I go 2, 3, 4, 5, 6.
So we've seen the first 4 terms. There they go. I don't know what 15.4 is on. What is 15.4 on? 15.4 is on one of the best fucking theorems ever. The binomial theorem, which has Pascal's theorem in it, Pascal's triangle in it. Pascal's triangle is a fucking work of art. It's just the numbers, you write the numbers in a triangle shape. It's not related to triangle at all. Or it doesn't have to be.
Isn't there kind of a theory that it also is geometric itself? It has like some geometric quality to it.
Well, you're doing exponents just like this.
See,
Next one. A sub 1 equals 3. A sub k plus 1 equals 4 times a sub k plus 1. This is called a recursive sequence. Each term depends on the term before it. So if I've got a sub 1 and I want a sub 2. A sub 2 is like 1 plus 1 down here. Which means k equals 1. So it'll be 4 times a sub 1 plus 1. Does that make sense? And when we do it, I'll just write the next few. A sub 3 is going to be 4 times a sub 2 plus 1. A sub 4 will be 4 times a sub 3 plus 1. So each time you're taking that previous answer and plugging it in. And I just didn't write 3 as 2 plus 1 and 4 as 3 plus 1. Because I know you guys can do that. So this was a sub 1 here was 3. So 3 plus 1 is 4. This is 16. Ah, Jones. You just fucking came up with this formula all on your own and you didn't even fucking see how big these numbers were gonna get. This was a Jones fucking failure. That's a sub 2. Which means that's what's gotta go in this son of a bitch right here. Now I gotta do 4 times 17, and I think that's 68. Seventeen, 34, double 34, 68, yeah. This will be 4 times 68 plus 1. 4 times 69 is 240 plus 36 is 276. That is much easier to do as 4 times 60 plus 9. 240 plus 36. That's what I did. That's how people, other than like human calculators, which I'm not. That's how you do a higher multiplication in your head quicker.
People who can do that stuff blow my mind. I don't know. It's wild. And they just like it just.
Just give them like a fucking 2 5-digit numbers and say multiply these and they immediately just spit out the answer. Yeah. So that's a recursive sequence. They actually, or at least have heard of a recursive sequence. The Fibonacci sequence is a recursive sequence. A sub 1 is 1, a sub 2 is 1. A sub k plus 2 equals a sub k plus 1 plus a sub k. And you end up getting 1, 1, 2, 3, 5, 8, 13, 21, 34. And it's a famous sequence. You're just adding up the 2 numbers before it. I want to show you a little bit more with factorials to just introduce the concept. Let's do some more with factorials because they do show up quite a bit in this stuff. Those series I was telling you about with that make light waves and sound waves into polynomial functions have factorials in them. So they're like, they show up in this science shit. So like, let's look at what is 3 factorial over 5 factorial. A way to do this easier is to take the bigger factorial and keep writing it until you get in terms of the smaller factorial. So the 3 factorials cancel out, we're left with 1 over 5 times 4, which is 120. These can cancel. Let me give you guys one fun to do. See what you come out with. Actually, my graduate work was harder than this. This doesn't have magnetism in it. This is fluid dynamics that are non-magnetic. The sun is made of magnetic plasma though. And I was doing astrophysics.
Measuring the magnetism of the plasma. That's fact.
By the strength of the pull.
Well, that's good. Yeah, it's, yeah, you can actually just measure it straight up.
How else do you measure magnetism? By how much it pulls?
Isn't it the case that plasma flows like liquid does? I mean, that's the same kind of like physical.
Very similar.
And that's the wildest thing to me, that like,
In fact, every single state of matter does that except solids. Because air flows like liquid as well.
oh, really?
Yeah.
But
In
you
fact,
can-
air is considered a fluid.
But you can kind of, but with air though, it's easier to direct than liquids. Like,
Is it? The way you would direct air would be with a fan? Can't you do that with water? It's called a propeller.
yeah, I was gonna say, it's all still propellers and tubes, yeah. It's all, yeah, you move into that wind tunnel, yeah, it's like that giant wind tunnel.
Yeah.
It's still tubes with propellers at one end, yeah.
Alright. So I'm gonna match up the 3 with the 2. And I'm gonna match up the 6 with the 5. Looks like I'm left with 3 times 6, 18. Because that will cancel that and that will cancel that. Now, you could write them all out and then cancel everything out. Or you could put this in a calculator, do it in a calculator, but I don't recommend it. Because what happens when you can't find the pattern with a calculator? You will not find patterns with a calculator. Not with something like a factorial involved. What about? N factorial over n plus one factorial?
You can distribute the factorial.
What do you mean by no, it is not distributive.
It's not distributed.
So if I were to write the top one, what would I write it as? N times what? Well, what if n's like 10? 1 isn't the next number.
0.
You're just guessing. Don't guess.
Yes.
What would be a number lower than the next number lower than n? When you don't know what n is.
1.
No. N minus 1.
Oh.
This seems obvious when you hear it, right?
Yes.
You're like, what, duh? I feel like it sounds really obvious. It does. So this would be like n minus 2. And then we would get down to, 4 times 3 times 2 times 1. Here, what's the next lowest number after n plus 1?
Just n.
Just n.
So
Which means I probably could have done this a lot shorter by saying n over n plus 1 times n factorial. And this just condenses down to 1 over n plus 1. Practice with factorials.
are technically all factorials reducible in this way.
Some of them are not as obvious. I'm not gonna go through the math of what to do with it. But for example, if you have like 2n minus 1 factorial over 2n plus 1 factorial. Well, I guess it should be kind of obvious. I don't know, what fucking John. Mr. Blakely in his textbook fucking goes, let's do this by example. No, fuck that. This is 2n plus 1. 1 less than 2n plus 1 would be 2n. And 1 less than 2n would be 2n minus 1. And now all of a sudden I match what I got on top. He went through like try n equals 1, n equals 2, n equals 3. What? Seemed very flawed in his logic, but I didn't think about it right now. What was wrong with that thought? So yeah, you can kind of do even with like multipliers in there and shit. You can do as long as you can see the connection between the two factorials.
So in this situation, you would, if you like, if you had like 3n minus or 3n plus 1, you just carry the 3 into this pattern.
Yeah,
But it's still.
well, if I have like 2n on top and then 3n on bottom. That now all of a sudden shit changes, because depending on what n is, these are drastically different.
But if they're the same, then you can't. You can just, since they match, since it's 2n to do the same pattern. And take it all.
Yeah.
So
Okay. So next topic in this section. We're gonna spend longer on 15.1 than we do on 15.2. Because 15.2 is pretty fucking easy. It's added, I mean. How hard does adding get? Series. Series is the sum of the first n terms of a sequence. I'm not defining what terms I did. I defined terms. I wrote terms of the sequence. I'll make sure I'm fucking being consistent.
You defined it for us, as I said earlier.
Yeah. The way we denote it is we have this symbol right here. And we will use something like this. That's my eye, in case you don't know what my eye looks like. If I draw an eye with like a normal eye, it looks like a 1 real fucking quick. This is a sub 1 plus a sub 2 plus a sub 3 plus a sub n. The I right here, that bad boy, I is called the index of summation.
What is the E?
The what? Oh, E is sigma, capital Greek letter. And the way I tell it to my students, it means add shit up. That's what it means. You see it, it means add shit up. The 1 and the n are really what's more important. It's telling us to add the a sub I. Add shit up, add up a sub i's. From I equals 1 to I equals n. So the n up top is called the upper bound of summation. Summation has 2 n's. And this number right there is the lower bound. Even though the upper bound doesn't show it, it really means I equals n. We tend to not write the I equals part, we only write it on the bottom. And the way you're gonna frequently look at a lot of this shit is the index of summation tends to act like the variable. As you'll see in a second. Oh.
It's not the same thing as the imaginary time. Or the complex.
Correct.
So you're different.
In fact, we don't even need to use I. I can very well do the same thing here. I can have sum of k equals 1 to n. So the index can be any letter. This is what happens when you try to pack shit in at the bottom of the fuck page. Write for me small, my minions. When you see the sigma symbol, they will tend to, the words that are often used are sigma notation. But it really means summation notation. We'll do some examples. I want you to see how it goes. Let's take a look at one example real quick before we start going into some properties. I equals 1 to 5. 3i minus 1. This is 3 times 1 minus 1 plus 3 times 2 minus 1 plus 3 times 3 minus 1 plus 3 times 4 minus 1 plus 3 times 5 minus 1. Where I'm just taking the I and going I equals 1, then 2, then 3, then 4, up to the upper limit, to the upper bound. So I equals 1 there, I equals 2 here, I equals 3 there, I equals 4 there, and I equals 5 there.
So it's kind of like, so this is kind of like a modified. Exclamation point.
No, it's not like a factorial.
It's not like.
It's factorial is multiplying, this is adding. I see where you're going, yeah, it's. The one where it's multiplying is actually a giant pi symbol. Yeah, it's fucking stupid. I don't know who the fuck came up with this. Yeah, we're not doing that in this class.
It's a giant I symbol.
Yeah, it's very like, I'll show it to you. Like if you see I equals 1 to 5 here, say I. It's 1 times 2 times 3 times 4 times 5. Which would end up just being 5 factorial here.
Yeah.
But sometimes you can't write this as a factorial. So like, I'm gonna scribble that out because I don't want that fucking cluttering up anyone's mind. We don't need that shit. I don't remember even using it that much, to be honest. And I went very deep down the rabbit hole of mathematics. So this ends up being, this is 3 minus 1 is 2. Then we got 5. And you'll see this was the first sequence we did earlier. Ooh. As soon as I said sequence, I started putting commas in. This is 15 plus 25 looks like 40. Yeah. What?
It's just I've got music playing in my head from someone mentioned that this is a signal.
Do you guys see how it works now?
Stop that.
Does that like, is the example kind of clear? You're going for, you go in order from the number on the bottom to the number on top, plugging in and then adding up each thing. It turns out there's some properties or formulas that can speed this up. So I equals 1 to n. I'm gonna start writing it like this. Because it's a little bit lower and it doesn't take up as much vertical room. If you see me write it like this, it means this. If I do that, c times a sub I, you can actually factor out the c. I'll just write it fucking normal. I don't need to be fucking. Put the numbers on top and bottom rather than on the side. You will see it like this in textbooks. In fact, I'll show you.
So that would be C times sigma AI.
Yeah,
That's what. Oh, so like C multiplied by like in that last problem, it would be like C times 40 to the very.
exactly.
So C is just another, it's just another value.
C is just another value, yeah. So like, if you're looking at Mr. Blakely's shit. He writes them to the side because it just flat out takes less room vertically. To write it right next to the things than it is to put it like this. This is more room vertically than this is. So that's the first property, so like it's distributed kind of thing. And it's because if you want to see it out, it's CA1 plus CA2 plus CA3 plus C or plus dot 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 plus CAN. And then I could factor out the C. But this is how I define. Okay, make sense? So with C times a function, you can pull the C out. Let's look at some basic one functions. You do I equals 1 to n of 1. This just ends up equaling n. Because you're adding up 1 n times. And the only reason we bother to say this is like, it relates to this one up here. So if I have like C. Like say it's 10, C is 10 or like 9. Let's say C is 9, we're going from 1 to 5. This is just C times I equals 1 to n of 1, which is C times n. So if you're adding up a constant a bunch of times, it turns into multiplication, as we knew. We know that. We know repeated addition is multiplication. So other fun ones. I equals 1 to n of I is actually a well-known formula. N times n plus 1 over 2. To be honest, that's the only one I have memorized. We have this one and the next one. The next one is I squared. It's similar. It's got a, let's see, I'm over here looking at it. N plus 1. It's got a 2n plus 1 and the bottom 6. Yeah,
For the previous form, in the green. Would that, it says C times whatever's in parentheses. You wouldn't want to calculate that amount first and then multiply that by C. You'd want to distribute the C, right?
I would probably just do this and then multiply by C. Why multiple, if I multiply first, then I'm adding up a bunch of big numbers. Or I could add up a bunch of smaller numbers and then multiply once.
So, but I
It's really a matter of choice.
guess it's the same.
The result is the same. So I could have done that 3 n. Oh wait, one more roll I want to show you. If we're adding up A sub k and B sub k. Adding or subtracting. This turns out we can treat it as adding or subtracting the individual summations. I guess I should write k equals 1 to n, k equals 1 to n, k equals 1 to n. This shit's this series notation. You'll see, I'm gonna say the first week of calculus, but it might be the second. I've taught it, I just don't remember what day I teach it.
It's good.
What day, it comes up early.
Yeah.
You'll see it early as an indicator where you're going. A lot of times, this is how the shorthand notation of how intervals are done, and intervals are like 1/2 of the heart and soul of calculus. Let's take a 5-minute break. I realize I haven't given you a break. We'll do some examples with this. And then we'll do arithmetic series. Let me hit pause. But they have no fucking armor. No armor. All right, so like we just had the 3n minus 1, we added up 3i minus 1. And we got the 40, right? So we did the 1 to 5 of 3i minus 1 and we got 40. Can we do that here? I can break this up into 3i minus the summation of 1. I equals 1 to 5, 1 to 5. I can factor the 3 out. This told us this was n times n plus 1 over 2. 5 times something's off here. Five times 6 over 2. Minus, this was just 5, it was n.
Oh, the n in that case being 1.
Right,
Or if that wasn't sigma 1. If it was like sigma 2, it'd be 5 times 2 or something.
right. I'm checking to see if I added, is that right? 15 and 25. It's 40. Let's see, I've got 6 and the 2 cancel here, leaving a 3. I've got 15 times 3 times 15 minus 5 is 45 minus 5 is 40.
Why did we subtract the sigma 5 1? Let's go on.
That is following this thing right here. We can break it up into 2 sigmas. Now, granted, I think redoing this was easier.
Yeah. I'm gonna say. So you can go either way with it.
Yeah, you can use either way. The formula only speeds it up. I'll show you one more formula.
And this will all be in Alex. Or
What
this is all in Alex too.
should be. Now, for me, I would do this. This is what I would do. 1 minus 2 plus 1. This is 4 minus 4 plus 1. This is 9 minus 6 plus 1. This is 16 minus 8 plus 1. I would calculate what each of these is. That's 0, that's 1. That's 4. That's 9. Wow, it's the fucking squares. Holy shit. Now I wanna see. Son of a bitch, look at this. I deliberately chose this formula for this. Because I wanted, I didn't work out what it was. This is n minus 1 squared. I'm like, wow, the fucking squares are showing up. But if I was adding up the first 4, I would have had 14.
And so you couldn't. So you couldn't move the square through and it'd be sigma n minus 1. You couldn't move, I guess you have nothing to move.
What do you mean?
So you couldn't like put 1 squared in front of the sigma. And just have it be sigma n minus 1.
No,
That might be what I'm saying. It would be actually more like if, well, an n minus 1 in front of sigma.
yeah, we can't pull up, if there's a letter that's related to the index. You cannot pull it out.
And, okay. Oh, n minus 1 go up.
No, because it's got an n and the index is n. If I have like a fucking k in here with the n,
Then you could.
and I could pull out the k, I could do the k.
Or leave this as a.
Or if it was like n minus 1 times k minus 1, I could pull out the k minus 1. So if that was the summation, it would be that summation. And I could do k, and we're doing n on these. I could pull out the k and leave that. Because this is really a constant compared to n.
And yeah, and this is, and the summation n equals 1 at the bottom is. Is the largest number of the sequence.
No, here I'm using n as the index of summation. So whatever number I'm going up to, let's say it's m. So maybe I should have used I if you like I better. Here n is the thing we're treating as a variable. It's the index. The other way of doing this is breaking it up into n squared minus 2 times n plus 1. And we're doing 1 to 4 on each of these. And we had a formula for n squared, or the squared one. It was the upper bound times the upper bound plus 1 times 2 times the upper bound plus 1 over 6. That was the n times n plus 1 times 2n plus 1 over 6. That's that one, and I can say minus 2 times. This was n times n plus 1 over 2. That's the summation for n. And this last one is just 4. This seems like a lot of work when this was pretty easy, right? Like, cause here now I gotta fucking clean it up. This is 4 times 5 times 9 over 6. Minus, n here is 4. So 4 times 4 plus 1. 2's cancel. Minus 4 times 5 plus 4. 4 times 9 is 36. This is 36 times 5 over 6. That simplifies to 6. So I've got 6 times 5 is 30 minus 20 plus 4 is 14, just like we had it here. But that's a lot of fucking work, right?
Yeah, yeah.
Ah.
That was, it's almost.
Right, I just think the top one's easier. Now,
Cause you
if we're going from like 1 to like fucking 100. I don't wanna do this fucking 100 times. So it's like, how many times do I gotta do it? Like, you know what I mean? If I had to do this even fucking 20 times, I'm tapping out, like this is a little bit quicker. Well, maybe 20, I'd be like, nah, fuck it, let's do it. But like 50 times, no, I'm using the fucking formula. So the more you gotta do it, the more it's better to do the other way. Alright. I can make this 2 videos. Stop and start.